So we're going to talk about PervNERT, PV equals nRT or PervNERT. You've heard, if you think back to your chemistry days, this is the ideal gas law. And in the ideal gas law, so this is important to note, this is only for ideal gases. You can think of these are the gases that behave under ideal conditions, which all make up this last column up right here on the periodic table. This has to do a little bit, the chemistry involves a little bit to do with the fact that their valence shells are full. We're not going to go into too much of the chemistry for this. That is part of the physical science, the second course of the physical science class, not for this one. But that being said, we're going to look at how the ideal gas law can relate to the ideal gases. Why is this part of fluid dynamics? Gases are considered the same in terms of mechanics and how fluids move and behave, essentially. The only difference with the ideal gas is it's compressible, whereas like fluid like water is incompressible. But I could lower the temperature on a gas or lower the pressure, like think of a deflating balloon, or if you put a balloon in a refrigerator, it shrinks. It is compressible, and part of that has to do with the energy level of the particles, the elements, and the individual atoms. But again, we won't go too far down the chemistry rabbit hole. We're going to look at an example using PV equals nRT for helium. Helium is a really good example, and one of my favorites for ideal gases, partly because helium is used and produced in stars and nuclear fusion. But it's also the second element on the periodic table. So helium's atomic mass number is atomic weight, I think that's just the term, atomic weight, AMU, is 4.0026. And what this means is this is how much its mass is per every mole. And mole we can think of as each individual particle, each individual one is a mole, each individual unit. And we're going to use this in terms of the PV equals nRT equation to understand how this could relate. So P is the pressure. This is going to be in units of pascals. So this is pressure, which is going to be in pascals, which we already noted is newtons per meter squared. That's the unit for pascals. So it's important to understand when we are actually calculating this. V is going to be volume. This should be in meters cubed. Then N is the mole count. So this is the mole count. Its unit is moles, M-O-L. We drop the E just for brevity. R is the ideal gas constant. It's 8.314 joules per mole Kelvin. But if we remember, a joule from back in our work energy days is just a Newton meter. So I'm going to rewrite it as 8.314 Newton meter per mole Kelvin. And then the temperature, T is the temperature. This is going to be in Kelvin, which is represented with K. Let's say we want to find the pressure in a balloon. Balloon isn't a perfect sphere, but we're going to estimate it to be about a sphere. Again, this is theoretical. We can kind of come up with it. We'll say that the radius of this balloon is 20 centimeters, or the radius is 20 centimeters, which would be 0.2 meters. Okay. And so that gives me a volume for the balloon of 4/3 pi r cubed. That's the volume of a sphere, and approximating that the balloon is going to be a sphere or spheroid, sphere-ish. 4/3 pi, this would be 0.2. The meters in there would be cubed. Sorry, meters, all of that cubed. And this is very small volume, but you got to remember this is in units of meters, so it's going to be tiny. Balloons are small with respect to meters. Usually we would use centimeters or millimeters, but for ideal gas law, we're going to keep it in meters. This an estimated volume or approximate volume, 0.03, we'll say This would be meters cubed. I'm going to keep a few extra significant figures here for this. And we want to say that this balloon is sitting in just the room, right? So maybe standard temperature of 75 degrees Fahrenheit. So we're going to convert our 75 degrees Fahrenheit using the Celsius equation to Fahrenheit. So Celsius is equal to 5/9. The Fahrenheit degree, so that's 75 minus 32. How we convert. I really wish it weren't that random. It seems kind of random. I really wish we just use Celsius like the rest of the world, but that's an argument for another day. This is going to give me 59.44 degrees. You'll notice this is in Celsius. I actually want Kelvin, but Celsius to Kelvin is a very simple conversion. Kelvin is just going to equal the Celsius plus 273.15 degrees. So we're going to do 59.44 degrees plus 273.15 degrees. And that's going to give me my Kelvin. I get standard room temperature, 332.59 degrees Kelvin. So that's going to be the temperature of our essentially balloon full of helium. And let's say we put in about 20 grams of helium. So let's say we put 20 grams of helium. Using the atomic mass number, we can figure out, well, how many moles does it have? If I have 20 grams of helium, this is where stoichiometry comes in, and literally stoichiometry is what it's used for. This is the grams, and then this will be the mole amount. For every 1 mole, the number I have, the 4.0026, sorry, it's so small, that's grams per mole. So I'm going to take this 20, and I'm going to divide the atomic mass unit. And I get that's approximately 4.9967 moles of helium. Now I have all my parts. If I wanted to figure out how much pressure would be in this balloon using PV equals nRT, I'm going to divide our volume to the other side. I get the pressure, which I should expect the units to be pascals or Newton per meter squared. So that should be our end unit when we cancel everything out. This is going to be the mole content, the ideal gas constant, the temperature over the volume, which in this case, mole amount, that's going to be 4.9967 moles times the mole constant, 8.314. I'm going to write it as Newton meter per mole Kelvin. The temperature in Kelvin, because it has to be in Kelvin to cancel out with the ideal gas constant. Now, sometimes you can use an ideal gas constant that has different units. We're going to keep it standard. The less numbers we have to memorize, the better. This is going to be 332.59 Kelvin. All of this divided by the volume, in this case, the 0.0335 meters cubed. And let's go ahead and calculate that. We actually get a somewhat large number, but that's actually sort of understandable. It's going to be 4.12, we'll say 4 times 10 to the 5. In this case, my units, let's double check that the units cancel out, that I really do have pascals. I've got moles that cancel. I've got Kelvin that cancels. I have newtons that I want to keep. One of these masses will cancel, and I get Newton per meter squared. So that looks good. That is the definition of the Pascal. And just to put this into perspective, the atmosphere standard, now again, it varies, but generally at sea level, standard atmospheric pressure is about 101,325 pascals. To kind of put this into context, this is about 4 times atmospheric pressure. That would be about 4 times as much atmospheric pressure inside that balloon, which is somewhat reasonable. It's not completely reasonable. It definitely would strain the rubber, which is actually why it blows up and strains like that. But that's something we would standardly see.